Hello, welcome to Physics 450. This is our first recorded lecture. Okay, so our course is about Introduction to Solid State Physics, and with you is the instructor for this course, Lina Abdulhamid. Important announcements before I go forward. We will have live classes every Tuesday at 12:30 p.m. Okay, for those of you who contacted me that they have work at this time, all live classes will be recorded and I will be uploading them on Google Classroom so you can open them whenever you are free. Attendance of live classes is actually mandatory. So even if you have other reasons and you cannot attend classes, you have to make sure that you can attend 5, 6, 7 lectures throughout the course, because this will go into your participation grade, okay? To join the live classes, you can either press on the following link, which you can find on the stream, on your stream of the Google Classroom, okay? It will be the same throughout the course. Or you can just open Zoom and use this meeting ID and passcode. Again, this will be the same throughout the course. So this will not change. So anytime you want to attend a class, you go to the stream and you just click on the following link, or you copy this meeting ID and passcode, and this is how you will enter the class. Okay. Main references for this course. Actually, it is very, very difficult to find just one book and say, this will be the reference or this will be the book for this course. In here, I'm just focusing on, I'm just mentioning the 3 big books that usually are covered in a similar course. So this is the course by Simon, by Kittel, and by Ashcroft and Merman. As for you, I will be providing lectures with lots of notes and that you can actually use instead of using a book, okay? But if you would like to go to a reference book and to check extra problems by yourselves, or if there is a point that is not clear in my lectures and you wanna check it thoroughly, you can go to one of these books. Actually, I attached the book by Charles Kittel, Introduction to Solid State Physics, on Google Classroom. So if you go to course references, you can find this book over there if you want to do some research on your own. Otherwise, the material I will provide during the lectures should be enough, and you wouldn't need to find other sources, but it's completely up to you. Okay, just something very, very quick. I want to remind you I want to remind you of common states of matter that actually we took since we were still in high school, okay? So we studied that matter states of matter are gases, liquids, and solids. And if you remember, we said that gases, they have molecules that have no particular order, and they move freely within a container. However, liquids, they have no atomic or molecular order, so it is the same way, but they assume the shape of their container, okay? So do you remember these things from high school? As for solids, they have molecules that are tightly bound to each other. They're either regularly tight, and these we call them crystalline material, or they are irregularly tight, and we call them amorphous materials, okay? The study of liquids and solids is called condensed matter. But in this course, we are only talking about solids, and this is why our course is solid state physics. So we will only focus on solids. So what is solid state physics and why do we study? Before I cover this, I'm going to tell you that for this class, you're going to need a little bit of quantum mechanics. It won't be so much, The prerequisites for this course include just bits and pieces of quantum mechanics. I'm not sure actually what is the background. What's your background on this? So have you taken some quantum mechanics before or not? But what I can tell you is that I will be reviewing a little bit of quantum mechanics during upcoming lectures. So whenever an idea of quantum mechanics shows up in one of our lectures, I will be reviewing it a little bit so as you would know what I will be talking about. So what is solid state physics and why do we study it? So solid state physics is a branch of physics that deals with practical and theoretical investigations of the properties of solids, such as their superconductivity, their ferromagnetism. In other words, it's that the study of solids through various methods like crystallography, quantum physics, electromagnetism, mechanical properties such as hardness, elasticity, thermal properties, optical properties. So it's through studying these through solid state physics that we know more about these properties. And in particular, we can say that solid state physics is the most important branch of condensed matter physics because it helps us investigate the large scale properties of solid materials, such as the ones I've just mentioned, from their atomic scale properties. In other words, I get a material, I try to learn about its atomic scale properties, and from that, I will know how are the optical properties varying, what are the mechanical properties of this material, okay? Okay, now, what are typical types of solids? Solids are actually made of three types. It can be completely amorphous, or it can be polycrystalline, or it can be crystalline. And in the coming slide, I'm going to show you exactly how do these things look like. Each type is characterized by the size of ordered region within the material. So for example, if there is no ordered region whatsoever, this is an amorphous solid, okay? If there is some ordered region plus some not ordered region, this is a polycrystalline material. If the whole material is crystalline, then we say it is single crystal. If the whole material is ordered, then we say it is a single crystal. What is an ordered region? It's a special volume in which atoms or molecules have regular geometric arrangement or periodicity. So let me show you an example. Look over here. If you look at this object, okay, so if we look at this solid, we see that there is no periodicity whatsoever, okay? An example of that is glass. So an amorphous solid is coming from the Greek word a and morph. A means without and morph means shape. So it is composed of randomly oriented atoms, ions, or molecules that do not form defined patterns or lattice structures. Example of that is glass, like here, or plastic or rubber. Single crystal, it comes from the Greek kristallos, which means ice. It has an atomic structure. So if we look at the atomic structure, it repeats periodically across its whole volume. So if we look here at the red dot, we see that it is repeated periodically, okay? It is repeated periodically. The same thing about the blue region. The same thing if I take this square. If I take this square over here, I see that it repeats itself here, it repeats itself here, it repeats itself here, okay? So it's an atomic structure that repeats itself periodically across the whole volume. And this is an example of a single crystal that this is a real single crystal you can grow in a lab, okay? Or it grows by itself. Then There is the third type of materials, of solids, and that is the polycrystalline. So the polycrystalline, this is one example here. It's a material made of an aggregate of many single crystals called crystallites or grains. So you will see in some places, you will see single crystals, in other places, you will see like not so very well ordered material. So if we look here, you will find some parts of it are crystalline, parts of it are not crystalline, look like as if they are amorphous. Okay, so it is called polycrystalline because it has many singular crystals packed together. In this course, actually, we will focus on ideal crystals. Okay, now what do we mean by ideal crystals? We mean by ideal crystals those that have infinite periodic structure. So there is one periodic structure that keeps repeating itself. There is no impurities, there is no dislocations, that is, there is not one atom moving, changing its location along, it's in the periodic position, it is not in another position. There will be no vacancy defects, that is, there is no missing atoms. There will be no interstitial defects, that there is no extra atoms. Okay, so these ideal crystals, they have periodic 3D arrangements, they have characteristic geometrical shapes, okay, cubical, hexagonal. We will see other types throughout the course. They can be easily studied and modeled, and they have interesting properties for technology. In addition, they will be like fascinating, like jewels. Now, why do scientists care about dealing with studying ideal crystals? From a research viewpoint, especially when creating new materials, scientists want to remove as many variables as possible to understand a material's property. So a primary way to do so is to begin with raw materials that are as pure as possible, and this will allow them to produce materials as single crystals. Okay. Some beautiful jewels that appear in naturally, we can find on this slide. So we can find the opal, the peridot, the ruby, the sapphire. Perhaps you are, you know the diamond, the emerald, the crystal quartz. Okay, so these occur naturally around us, and these are single crystals. Other single crystals that are also found, these are like diamond. It is very well used because of its hardness. Lithium, these are used a lot in batteries. I don't know if you hear now about solar cells that solar panels that people are putting in their houses, especially these days because we are having problems with electricity. So people are tending to install solar system in their houses. For that, they need to put solar panels on the roof of the building, but they also need batteries in order to store light during the day and give us energy during the night. And the best batteries so far are the lithium batteries. Okay. Silicon is very well used in semiconductors, quartz in piezoelectrics, copper as conductors. Okay. And the more singular crystals they are, the better their functioning is. Overview of the course. What are topics that we will be dealing with in this course? We will start with crystal structures in 2D and 3D, okay? Of course, in the very, very beginning, I will introduce it in 1D, although there is nothing called a crystal structure in 1D, but we will see how we can move from 1D to 2D to 3D. We will be discussing topics like lattices, Miller indices, X-ray diffraction from crystals and the crystal structure determination, phonons in monoatomic and diatomic crystal vibration, phonons, defining phonon density of a state and modeling the specific heat of crystals. We'll be dealing with a free electron Fermi gas. We will be covering also, I hope we will have time to reach the topic about band structure, energy gaps, and block functions. So this was just a very quick introduction for our course and an overview of the material that we will be covering. And starting next time, we will immediately start with the first topic, which is chapter 1, which is crystal structure. Crystal structure. So in this chapter, we will be covering topics like lattices, bases. I will start with basic definitions that will help us to understand bigger things. So we will be dealing with introduction to definitions like what is a lattice, what is a basis, what is a primitive lattice vector, what is a unit cell, how does a Bravais lattice look like in a 2D, in a 3D. We will be focusing on cubic lattices, and these are simple cubic or body-centered cubic or face-centered cubic. We will be talking a little bit about hexagonal unit cells. We will be dealing with famous crystal structures. These are simple crystal structures like sodium chloride and cesium chloride. These are typical ones that many other structures have exactly the same structure as them. We will cover symmetry operations, and we will cover crystal directions and planes in addition to Miller indices. So in general, this is what we will be covering in this chapter, and this will be throughout around the 3 weeks. Okay, so don't worry, it's not like all these will be covered in one lecture. No, this will be covered throughout the coming 3 weeks. Okay, so by this, I reached the end of our first lecture. As I discussed with you on Tuesday, this is a course where it's not only me giving you information and you are just copying this information and memorizing it. No, I would really love it if we, because this is a very small class. We are only you're only 4 people in the class. So I would highly appreciate it if when you attend the lecture or when you go through one of the recorded material, you try to do some research on your own. Like you try to go, for example, and see how does a single crystal look like, and you Google it. You will find lots of YouTube videos that will show you that will show you animated stuff, so you can see how a single crystal really look like in reality. So this is really a topic which is very big, and we will not be able to cover exactly every single thing in this course. So I highly recommend it that you go through that you do your own research and you study more about the properties of solids. And come back to me with questions. Come back to me with questions that maybe I didn't cover in class, and then we can do that during one of our live sessions. Okay, so that's it for our first lecture. In lecture 2, I will jump immediately into chapter 1, which is a crystal structure, and it will be mainly few definitions that we will be covering through this chapter. Okay, so I hope you're having a great weekend, and for now, bye-bye.